This is Mr. Anderson for Kellogg Community College, and we're going to be taking a look at sum and difference formulas for sine, cosine, and theta. Now there's the first thing I'm going to do is list all 6 formulas here, but the one reason to not skip this part of the video, because you're feeling like you can just look in the book and get those 6 formulas, is that I'll be teaching you some tricks to help you remember these formulas and also look for patterns in the way that the formulas are written. So the sine of alpha plus beta is sine alpha cosine of beta plus cosine alpha sine of beta. Now, what's nice about the way that the formulas are written is they're all written in terms of alpha beta alpha beta. You'll notice that the original equation had alpha before beta. So if you look here, you see alpha beta, and this is kind of a palindrome effect for sine, where, you know, forwards and backwards it's the same thing. So things will change only slightly when we go the sine of alpha minus beta. We're going to still have that alpha beta pattern occur, and I can just put these in here to show you that. Also, this will be a subtraction instead of an addition, because this is the difference of alpha and beta. So here's sine alpha cosine beta minus cosine alpha sine beta. Now when we look at cosine of alpha plus beta, this formula is still written in kind of an alpha beta way, but it's the cosine of alpha and cosine of beta minus, which is maybe not what you have thought, sine of alpha sine of beta. So unlike the sine formulas above it, these ones have cosine before sine, and the symbol is opposite of what you think. You would think that the symbol in the middle would match like the top 2 here, but it doesn't. It's actually opposite. And so here we have another cosine alpha minus beta. So this is going to be cosine alpha cosine beta plus, instead of minus, the sine of alpha sine of beta. And we're now going to do something completely different, because tangent alpha plus beta and alpha minus beta have very different looking formulas, but there's still some hints of the there's still hints of alpha beta like they were in these problems up here. For the first equation, the tangent of alpha plus beta is going to be tangent of alpha plus tangent of beta. And again, take a look at the left and right side, and you'll see that there's maybe an easy way to memorize that. And this would be 1 minus tangent alpha tangent beta. You'll notice that the symbols are different here, and if you can kind of guess what the next formula would be based on this pattern, this is going to be a minus instead of a plus. So, you know, the numerator of this fraction matches the formula here, and the denominator is the opposite. But you'll notice that that tangent alpha tangent beta still fits here. See, alpha beta alpha beta alpha beta alpha beta. Now we're going to need to kind of move away from this here, and you might be asking yourself, well, shoot, what do I really need these formulas for? And it's for a situation when we're looking for a theta that isn't an 35, 45 degrees, 60 degrees, or a multiple of 90 degrees. So for example, the sine of pi over 12 is really 15 degrees. And I would figure that out by taking my pi over 12, if you want to convert from, you know, radians to degrees. You multiply it by 180 divided by pi. And if you do your simplification there, this breaks you down to, or that's a 12, not a 2 there. So 180 divided by 12, because the pi is simplified to 1, is going to be 15 degrees. So we're trying to figure out the sine of pi over 12, or what is the sine of 15 degrees. Now you'll notice that the sine of 15 degrees is not on the unit circle. But what is on the unit circle is 45 degrees, and another thing that's on the unit circle is 30 degrees. So if we convert the sine of 15 degrees into an equivalent expression of the sine of 45 degrees minus the sine of 30 degrees, you'll note that I'm using degrees instead of radians, but if you wanted to keep it in radians, you would then say the pi of pi over 4, or the sine of pi over 4 minus the sine of, I should probably just really tighten this up here. There we go. The sine of pi over 4 minus the sine of pi over 6. Well, using the formula I got above, this means that my equation is going to be the sine of pi over 4 times cosine of pi over 6 plus cosine pi over 4 times sine of pi over 6. So this is just a mere application of the formula that we learned from up above. The sine of pi over 4 is square root of 2 over 2. The cosine of pi over 6 is 1/2. I'm going to be multiplying these together. The cosine of pi over 4 is square root of 2 over 2. And sine of pi over 6 is square root of 3 over 2. And so if I do some simplification, top times top, bottom times bottom, this is square root of 2 over 4. And top times top, bottom times bottom, this is square root of 6 over 4. And you can write it like this. You could also collect, you have common denominators here. So you can rewrite this as square root of 2 plus square root of 6 over 4 if you'd like. The book also factored out the 1/4 in an equivalent expression where it's written as 1/4 times the quantity of square root of 2 plus square root of 6. And really I'll just show you that each one of these has its validity here. They're all the same answers, and really don't mind which way you have it written. Just the big process is to use the formula correctly and then do your correct algebraic simplification. But this is the exact value, as there are no decimals and no rounded answers. The tangent of 7 pi over 12 is another way of saying the tangent of 105 degrees. And what I can do is show you that we can convert this into degrees. The pi's would cancel away, so 7 times, or simplify to 1 technically, 7 times 180 divided by 12 is 105 degrees. So this is like saying the tangent of 105 degrees. Now you'll notice that there is no exact value for tangent at 105 degrees, so we have to look at the table and our unit circle to find out what two units can add up to or subtract down to make 105 degrees. And the ones that I chose 60 degrees, and I also chose 45 degrees. So I made this into the tangent of 100, I was going to write 105 degrees. That's not what I said here. I want to put down the tangent of 60 degrees plus the tangent of, let's see, I said 45 degrees, and that will give me to 105 degrees. Or if you want to look at it this way, it's the tangent of pi over 3 plus pi over 4. So what I'm about to do is use the tangent formula here. So the tangent of pi over 3, which I can find on my unit circle, minus the tangent of pi over 4, which I can find on my unit circle, divided by 1. I think this definitely should be a plus. Sorry about that. I should have a plus there. And I should also have a minus here. There we go. And that is going to be tangent of pi over 3 times tangent of pi over 4. And we're going to get into a little tricky algebra here. The numerator is pretty straightforward because the tangent of pi over 3 is square root of 3. And the tangent of pi over 4 is 1. I'll probably be reordering that because rationals go in front of irrationals and so on and so forth. Than the imaginaries, but we don't have any imaginaries here. Now down below what we have is 1 minus the tangent of pi over 3 is the square root of 3, and tangent of pi over 4 is 1. So what we have here, if I reorder the top, 1 plus the square root of 3 over 1 minus the square root of 3. Now there's something back in Math 121 that says we can't really leave the answer this way because we cannot have a square root in the denominator. So proper mathematics tells us that we should take the denominator here, this 1 minus the square root of 3, and rationalize it. And the way to do that is to use the binomial and the opposite binomial, because when we FOIL it, the square root of 3's will be simplified. Now it doesn't seem that way from the numerator, and in the numerator the square root of 3's will not simplify actually, because if we FOIL the numerator, 1 times 1 is 1. 1 times square root of 3 is just square root of 3. Then 1 times square root of 3 is another square root of 3. And then square root of 3 times square root of 3 is square root of 9, or just 3. Now in the denominator, 1 times 1 is 1. 1 times square root of 3 is just square root of 3. Negative 1 times, or negative 3 times 1 is negative square root of 3. And negative square root of 3 times positive square root of 3 is negative square root of 9, or negative 3. So you see that the bottom term, or the bottom middle two terms, they do simplify to 0. So my numerator becomes 4 plus 2 square roots of 3 divided by 1 minus 3, which is negative 2. And what I will do now is I will divide each of these by negative 2, since this is a monomial denominator, so negative 2, negative 4 divided by negative 2 is negative 2, and 2 divided by negative 2 is just negative 1, or negative 1 square root of 3. So there is my answer to that. Again, some of you might leave your problem in this way, but we can't because of the square root of the denominator. So this is a little quick review of some Math 101 stuff, or 121 stuff, to get us through rationalizing the denominator using a binomial. Now, for the sine of 105, we just actually got done with, looking at 60 degrees and 45 degrees. So let's use this again, but we'll use this in terms of, sine and cosine according to this function here. So we've got the sine of 60 degrees, and you'll notice I won't be turning these back into radians here because, again, it won't matter. Cosine of 45 degrees plus, since we're adding in this case, this is going to be cosine of 60 degrees and the sine of 45 degrees. All right, so let's actually go to the unit circle here. The sine of 60 degrees is square root of 3 over 2, and cosine of 45 degrees is square root of 2 over 2. We're going to multiply these together. The cosine of 60 degrees is 1/2, and the sine of 45 degrees is square root of 2 over 2. We're going to be multiplying these together. And what this gives me is square root of 6 over 4, and what this gives me over here is square root of 2 over 4. So, again, this is going to give us the same results as this above. You see square root of 6 over 4, square root of 2 over 4. So again, we will have the same results as what's above, and because of the commutative property, I can switch this around. So your answer is going to be like this, or it can be like square root of 2 plus square root of 6 over 4. We're going to be 1/4 square root of 2 plus square root of 6. So you see now that the sine of 105 degrees is the same as the sine of 15 degrees. Which, I mean, if you take a look at the unit circle, you'll see that sines and cosines sometimes have synergies like that, where they match other values on the unit circle, and that happened to be the case. For this final problem here, I want to move my page down just a little bit because I ran out of room just using that little piece there, so this will actually make things a little bit better for us to see here. So the tangent of 195, the one I used the tangent of 150 degrees plus 45 degrees. What this is allowing me to do is I like using a plus versus using a minus. Again, you could have chosen an angle that was bigger than 200 degrees and subtracted some other angle from it to make your 195 degree angle, but I have preference for that. I think that this is a better way, but again, to each their own, as long as it's mathematically accurate and also is simplified correctly. One of the tricks about this problem is that the tangent of 150 degrees, if you look at that on the unit circle, is negative square root of 3 over 3. Don't forget the negative, that's easy to do. And the tangent of 45 degrees is 1. So down below we got 1 minus negative square root of 3 over 3 times 1. Okay, so what this allows us to do is it allows us to do a little bit of simplification. Negative square root of 3 over 3 plus 1, and then 1 plus, two negatives make a positive, square root of 3 over 3. Now we're not really close to simplifying this yet because the answer, first of all, can't be a fraction divided by a fraction, nor can we have square roots in the denominator. So the first step I'm going to do, which is a little bit different than problem number 2, is I'm going to get a common denominator. And to do so, I'm going to multiply this 1 by a 3 over 3, and multiply this 1 by a 3 over 3. In doing so, I'm following a very simple and actual legal rule of mathematics to get common denominators, where you multiply by 1, or a special 1 in this case, a 3 over 3, to get your answer. So let's take a look at this here. Now I have negative square root of 3 plus 3 divided by 3 all over, down below here, I've got 3 plus square root of 3 all over 3. Now, dividing fractions, please don't cry, just skip, flip, and multiply. We're going to take this first fraction and skip it, but I will take this opportunity to rewrite it. Skip the first fraction, flip the second fraction, and multiply. So these 3's will simplify to 1. So now I have this simplified answer. Instead of a fraction over a fraction, I got 3 minus square root of 3 over 3 plus square root of 3. Can't leave my answer like that. Just like in problem 2, I can't leave a problem with some kind of square root in the denominator. So we're going to do a FOIL trick of taking our denominator and multiplying by the opposite of that binomial. Just the last terms. Because if I make this somewhat of a difference of squares, like an a plus b, a minus b, what will happen is that my denominators will simplify very nicely. Now in my numerator, things are going to get a little hairy for a moment, because 3 times 3 is 9. 3 times negative 3 is negative 3 square roots of 3. 3 times negative 3 is negative 3 square roots of 3. And then finally, negative 3 times negative square root of 3 times negative square root of 3 is positive square root of 9, or we will just simplify that down to 3. Now down below here, what we have here is 3 times 3 is 9. I have a negative square root of 3. I have a positive square root of 3. And then I have a negative square root of 9. I'm going to do some simplification. In my numerator here, this is 9 plus 3, so that's 12, minus 6 square roots of 3. Now down here, these square root of 3 simplify. 9 minus the square root of 9 is like saying 9 minus 3, which is 6. And going through one final simplification, 12 divided by 6 is 2, 6 divided by 6 is 1, or 12 minus the square root of 3 is your answer there. Alright, well, hey, thank you for watching the first of, I think, 4 parts of this video? 2, 3... Yeah, I think 4 parts there. So thank you again for watching, and I appreciate the work.